Alright, so we start new section 11.1 vector functions of one variable. Okay, so what are these? So vector function of one variable is something like this. There's only one variable. Since we reserve x, y, z for the space components and we are talking about vector functions, so x, y, z will be the components of the vector function. Therefore, as the variable, we prefer to use something different than x, y, z. So we use t. So this vector has three components: x and y and z, x, y, z. Okay. So here both x, y, and t are functions from R to R, right? Functions from R to R. Okay. So this can be considered from a function from R into R3, right? Each point gives you a vector in 3 space. Example, for example, this gadget RT, which is t squared and t cubed. Okay, this is one example of a function. Another one, let's say 3 times cosine, let's say 2t, 4 times cosine 2t, and 5 times sine 2t. Okay, this is another example. We may talk about continuity and differentiability of vector valued functions. A vector valued function R t, which has coordinates. We can also write it this way: x times I, y times j, and z times k. Okay, I, j, k being the unit vectors along x, y, and z directions. Okay, so I is this vector, j is this vector, and k is this vector. Okay, unit vectors. A vector valued function is okay, will be continuous if its components x, y, and z are continuous functions, right? X, y, and t are functions of t. If they are continuous, then R is continuous. And similarly, it will be differentiable if its components are differentiable. Yani RT'nin continuous veya differentiable olması komponenti olan x, y ve z fonksiyonlarının continuous ve differentiable olması demek. Başka bir şey değil. So this is continuous if and only if all x, y and z are continuous, and this is differentiable if all x, y and z are differentiable. And if R is differentiable, if RT is differentiable at a point, let's say T0, then we write what? R prime T0 as what? X prime T0, Y prime T0, and Z prime T0. So derivative of R is just you take derivative of each component and then evaluate them at the point T0. If let's say RT is, so this is a space curve, something like this, okay? So let's say this is RA and this is RB. Suppose R is a space curve like this. At a point T0, let's say RT0, the derivative of this R prime T0 will be just the, it can be considered as the velocity vector, right? R prime T0 can be considered as the velocity vector uh, moving as RT. Yani vector of a particle whose position is given by RT. Yani RT bir nesnenin hareketini veren ifade ise, suppose we have a moving particle and RT is the position of the particle at time t, then R prime t is just the velocity vector. Why is that? Well, because, what is this gadget? This is, as usual, just the limit as, let's say, h goes to 0, r t0 plus h minus rt0 divided by h, right? This is usual definition of derivative. And what does this mean? Well, this is the position, let's say, at rt0, and this is the position at rt0 plus h. And you look at the distance between these two vectors. So this distance difference is just this gadget. So this is kind of the, difference between the positions, and then you divide this by the time difference and you let h goes to 0. So this is just, right, this limit is just the velocity, right? Velocity at t0. The length of the velocity vector, of course, this is just the norm of this vector. So this is just x prime t0 squared plus y prime t0 squared plus z prime t0 squared square root. This is, of course, is the speed, right? Speed at time t0. Velocity vektörünün boyu hız değil mi? The magnitude of the velocity vector is the speed. Okay. These are things actually you remember from physics also, but not all of you take physics, right? Do you remember from high school? No? O zaman bu dediklerimi anlamadınız mı? Hızı. Tamam. Ben hani az çok fizikte de görmüşsünüzdür diye düşünüyordum ama hepiniz fizik almadınız. Tamam. Okay. All right. Differentiation rules. It is always, helpful to relate this kind of concepts with physical concepts. You understand them better, okay? Moving particles and so on. Okay, now let ut and vt be differentiable vector valued functions, and let lambda t be a differentiable function, be a differentiable scalar valued, I mean usual function. Okay, not vector valued, but scalar valued function. Then ut plus vt. We may add these vector valued functions. We can multiply a vector valued function with a scalar valued function. We can take dot product of two vector valued functions. We can take cross product of two vector valued functions, and we can take composition of a vector valued function with a scalar valued function. You get different functions. These are all differentiable, and we have the following rules for the derivatives, namely derivative of the sum of two vector valued functions. This is just u prime t plus v prime t, as usual. D over dt lambda t times ut. So you multiply a vector valued function with a scalar valued function, you get a vector valued function. The derivative of this is again given by the Leibniz rule, right? Because we have a product. And what is the derivative? Derivative is this. You take the derivative of the scalar function, you get another scalar function. You multiply with the vector valued function, so you get a vector function. And then lambda t times derivative of this vector valued function, which is another vector valued function. So in total, this is again a vector valued function. So this is just the Leibniz rule. And we have Leibniz rule for scalar product also. If you take scalar product of two functions multiplied, then the derivative of this is just again given by the Leibniz rule. First derivative of the first function, and then scalar product with the second one, and then plus the first function times the scalar product with the second one. The same for the cross product. So again, this is just this function cross this guy plus this one cross the derivative of the second. So Leibniz rule just generalize to all kinds of actually products. And finally, this is just the chain rule. I replace t by another function of t, lambda t. And what is this? The derivative of this will be just derivative of u, and then you put lambda t here, and then derivative of lambda prime t. Lambda prime t is a scalar valued function. You multiply this with the vector valued function. Let me just prove one of them. Okay. Let's, for example, do part C. Just one of them. Ut, let's say this is just given by xt, x1t, y1t, z1t, and vt is another vector valued function, x2t, y2t, and z2t, right? Two vector valued function. We assume that both of them are differentiable. Well, then what is the dot product of these two vector valued functions? You take dot product of these two vectors. What is the dot product? Well, that is just x1. Dot product means you multiply the components of the vectors, right? First components, second components, third components, and then add them up. So this is x1 to x1t, x2t plus y1t, y2t. This is usual product, z1t and z2t. I want to take the derivative of this. Well, you just take derivative of this object. So you take derivative of each one separately. What is the derivative of the first guy? Derivative of this? Well, that is just x1 prime. This is the product of two scalar valued functions. So I apply the usual Leibniz rule. Derivative of the first one times the second plus the first one times the derivative of the second. So this is for this term. And then I have similar term for the second one. Derivative of the first one times the second plus the first one times the derivative of the second. So this is the derivative of the second term. And then we have the derivative of the third function, which is z1 prime z2 plus z1 z2 prime. And then we can do the following. You see, okay, I group this three terms. So x1 prime x2, y1 prime y2, z1 prime z2 plus the remaining ones, x1 x2 prime, y1 y2 prime, and z1 z2 prime. And then note the following. The first term is nothing but the dot product of these two vectors, x1 prime, x2 prime, not x2, y1 prime, z1 prime, dot product with x2, y2, z2 plus, what about this one? This is the dot product of x1, y1, z1 with dot product x2 prime, y2 prime, z2 prime. So what is this result? What is this then? What is this term? This is just, right? U is this. What is U prime? U prime is just this. So this vector here, x1 prime, y1 prime, z1 prime, is just U prime, right? U prime is just x1 prime, y1 prime, z1 prime. So that is U prime, right? So this is U prime t, and then this is just V prime, Vt, not prime, and then this is U1, no, Ut times dot product, I mean, x2 prime, y2 prime, z2 prime. Well, this is just V prime t. Okay, so that's the result we wanted to prove, right? We wanted to prove that gadget here. Dot product, derivative of the dot product is this gadget. Tamam mı? All the others are similar. I mean, for cross product, you have something similar. Of course, cross product is, messier. There are several terms, but it is just the same thing. All right. So the others are similar. I'll just drop it. Okay. Let's do some examples. Show that if an object has constant speed, then the velocity vector and the acceleration vector are orthogonal to each other. Okay, so if you have an object with a constant speed at any point, let's say RT, suppose you have at this point, you have velocity vector R prime t, or let's say Vt, velocity, and then we have acceleration vector. In general, acceleration vector doesn't have to be perpendicular to the velocity vector, right? If you just pull an object with a force, then acceleration vector and velocity vector are in the same direction, right? If you have a falling object, both vectors are just in the negative z direction, both velocity and acceleration. What does this tells us? The following: if the speed is constant, then these two vectors has to be perpendicular to each other. So in general, at acceleration vector is something not in the same direction with the velocity vector. But this tells us that if the velocity is constant, then they are perpendicular. Acceleration vector is the force, right, you feel if you are moving on this track. Yani bunun üzerinde bir arabayla gidiyorsanız ve pozisyon vektörünüz buysa, acceleration vektörü sizin hissettiğiniz kuvvet, değil mi? Böyle bazen sağa savrulursunuz, bazen sola. Acceleration o. Velocity de velocity vektörü işte, yani hız. So let's see why this is the case. What is speed? Speed at time t is, what was it? It was the norm of the velocity. So it is just the norm of this vector, r prime. Well, r prime is what? R prime, if rt is, let's say, xt, yt, zt, r prime, the velocity vector, this is the position vector, velocity vector is this. What is the speed? Speed is the norm of this. So it is just square root of x prime squared plus y prime squared plus z prime squared. Well, what is this actually? This is nothing but r prime dot product with r prime, and then you take square root, değil mi? Kendisiyle çarpımının karekökü. Yani normu dediğiniz şey, bu vektörü kendisiyle iç inner product'ını alırsanız, if you take inner product of this vector with itself, you get x prime squared, y prime squared, z prime squared, and then you take square root. Okay, now, so in our case, what is given? This speed is constant. So it is not a function of t. It is constant. It means this is constant, okay? Constant. So it means what? R prime t dot product R prime t is this constant squared. Well, that is another constant, of course, right? Now, what you do, just take derivative of this, d over dt, r prime dot product with r prime. Well, d over dt of the constant function, right? This is independent of t. T is changing, but this constant is not aware of it. Therefore, this is just 0, right? Constant doesn't change, so its derivative is 0. What about this gadget? Well, we used Leibniz rule. Derivative of the first one, well, it is the second derivative. Dot product with the first derivative plus the first derivative. Dot product derivative of this, well, it is the second derivative, and this is 0. However, dot product is symmetric, so a dot b is the same as b dot a, right? Therefore, I can write this as just r prime t dot product r double prime t plus r prime t dot product with r double prime t. This means this gives us r prime t dot product r double prime t is 0. However, r prime t is the velocity vector, and r double prime, change in the velocity. Change in the velocity is the acceleration vector. So this is at, the acceleration vector. And the dot product is 0. Well, dot product is 0 means Vt is perpendicular to at for all t. Yani mesela bir ipin ucuna bir nesne bağlayıp döndürün havada, right? If you, a typical example of this is as follows: take a rope, put an object, and just, you know, spin this like this with a constant velocity. Okay, the velocity vector is tangent to this, and acceleration vector is the vector along which you apply the force. Force is applied via, you know, this rope. So its direction is the line segment joining this point to the center. So this is the acceleration vector. And of course, this is always perpendicular to the tangent. Dolayısıyla the force you apply is always perpendicular to the motion. That's why you make no work. Değil mi? Böyle çevirirseniz hiç iş yapmamış olursunuz. Of course, if there is friction, then you make some job, but otherwise, no work is done. Boşa dönüyorsunuz yani. Tamam mı? Sorusu olan? Hı. Tabii, tabii. Acceleration is zero means you apply no force. In that case, of course, velocity doesn't change and speed doesn't change. So speed is constant. Speed vector is still perpendicular to the acceleration because acceleration is already zero, right? Perpendicular means the dot product of the two vectors should be zero. If one of them is zero, then they are perpendicular. Okay. Uh, Bir ara verelim. Aradan sonra devam ederiz. Let's give a break.